Welcome to AP Review Solutions number 11. One problem involving angular momentum, collision with something about a pivot point. So I consider this a particularly important problem, a good problem with a lot of parts to it, so nothing gets too involved. So just to recap, we have some disk that's moving, hits a rod that's free to rotate about this pivot point, and it hits it off the center of mass. And then they ask some questions going from there. Okay, the first question is, where would we want to hit it relative to C, or if we wanted to have as high an angular speed as possible? And then explain your reasoning for that. All right, so if I could scroll up to that. Basically, we want to hit furthest away from C as possible. All right, there's a number of ways you could do that. The simplest one is talk in terms of torque and then change in angular momentum. Basically, you would say the further away from C we hit, or further away from the pivot point we hit, the greater the torque. You could throw in there that torque is a force times some lever arm. Okay, and if you want to go a step further, you could say that the impulse from a torque, right, the tau times time equals a change in angular momentum, and angular momentum is related to angular speed. Okay, so you don't have to go too much detail on that if you look at the rubric. Okay, now things seem to get real complicated real quickly, but if you read carefully, this is not so bad. So on the internet, imagine that a student finds an equation given by this, and they don't want you to worry about right now if it's correct or not, but does it agree with your reasoning from part A? Okay, does the equation for, that should say omega, have the expected dependence? So if we argued that the further away from the pivot point we strike it, the greater the angular velocity, well, what measurement is that? Well, if you look on the diagram above, that's nothing more than x, right? That's our lever arm here. So we'd expect to see omega proportional to x, and sure enough, we see omega is proportional to x right there. I is staying constant, the mass of the disk isn't changing, nor is the initial speed. So that's a pretty straightforward way of explaining that, just looking at that dependence there. Then we have another equation that somebody else found, deriving it, that looks like this. And they don't want you to derive the equation, they just want you to look at this and say, does this make physical sense? Okay, and that word physical is actually pretty important, because one approach you could do, which they discourage, and I'm not sure how many points you lose, is look at this from a dimensional standpoint. Put in the units for each one and see if it comes out to be let's say radians per second. And that might be challenging for you anyway, so you might want to avoid that. But I would avoid that. What they're basically asking is, does it make sense that a greater angular speed would depend on distance? Yep, it does. Would it depend on a greater velocity? Yeah, that makes sense. Okay, would it depend on a greater a moment of inertia or mass? And that's really the key to this. Okay, so an easier one, I think, not so easier, is we could say no, it doesn't make sense, because this equation is suggesting that omega is proportional to 1 over the mass of the disk, not the rod. So what that suggests is if the heavier disk hit it, it wouldn't go fast, it would go slower, which doesn't make sense. So you make that argument, you've got 3 points. You could, this is also, you could take it from a moment standpoint, or both. You could say this is suggesting, whoops, that the moment of inertia of the rod. So if it had a greater moment of inertia, it would take off with a greater speed. No, it wouldn't. It would do the exact opposite. So it's those two factors, the I and the M, from a physical standpoint, that we can use to explain why that equation doesn't make sense. Okay, in D, now they want us to derive the equation for omega, and they give us a bit of information. They did us a favor by telling us that before the it had an angular momentum of mvx, and that's something that I'm gonna go to a new sheet here, that you may have forgotten, and you are expected, you could be expected to do that, to know that. So let me review something in general here. So let's, again, looking from above, here's our pivot point, here is our rod that's free to rotate. Okay, and again we have some mass coming in with some velocity and it hits it some distance away. I'll leave it as x, or it could be r. Right? Even though this is not rotating initially, this system, if we define a system as the rod and the mass, has angular momentum. Its initial angular momentum is due to this guy because it's moving perpendicular to the axis of rotation, and that would be the linear momentum of the ball times the r, right? That's a general equation for the connection between angular momentum and linear momentum is P cross r, and that would be mv x in this case. The cross just means we need a perpendicular component, and so it's already moving perpendicular. So that's where that equation comes from the original problem. And they tell us also, I believe, let me go back just to make sure I've got that right. They tell us something about the moment of inertia, all right? Okay, so the disk's rotational inertia about the pivot point is mx squared. Okay, and that comes from the mr squared general. In other words, it's not the rolling disk. This is just sliding, but since it's off axis, it has a moment relative to that pivot point, and it also tells us that the rod itself just has a generic moment of I. So we don't need to know the special equation like 1/3 ml squared or something like that. So if we go back to this, basically your derivation is pretty straightforward. You are conserving angular momentum here. If you take the approach of trying to conserve linear momentum, you don't get any points because linear momentum is not conserved. Linear momentum is not conserved because there's an external force to the system coming from the pivot point. They didn't ask about it here, but that's a really good question. Angular momentum is conserved because there's no external torques. If we define a system as the ball and the rod here, it's that any torque that this exerts on it is internal. So for sigma L, we were already told that's mv naught x. And then for, I'm sorry, this should be prime. Oh boy. For afterwards, right, you're going to have two parts. Well, I shouldn't say you have two parts. You have one system because they stick, but you have two moments you want to combine together. So the general equation for after is going to be an I omega, okay, but we want to then get more detail with what I are we talking about. So that's the combined moment of both the ball before and the rod. So that's going to become I, that's the rod's moment, and then mx squared, which was given, times omega. So then we can solve for omega, and we see that it is mv naught x all over I plus mx squared. And we don't have to simplify from there, and really there's not much we can do to simplify. Okay. Then it asks in E, suppose instead of sticking, okay, whoops, I think I missed mass. Does the rod have mass? Yeah, I might have need to include the mass of the rod in there. I don't remember seeing that, or maybe it was small compared to the disk. Anyway, suppose it bounces off, and they want to know, would the angular speed be greater than, less than, or the same? The answer is it would be greater than. And then you'd have to explain it. It doesn't have to be a super detailed explanation, but probably the easiest way to explain it is if it bounces off, the change in angular velocity of the disk is going to be greater than the change if it sticks, right? The one that's, I'm going to put the delta W naught, omega naught as the initial. And if there's a greater change in angular velocity, then you can relate that to a greater change in angular momentum, right? Where L is simply I, the delta L is I delta omega, and therefore you can argue a greater change in angular momentum means a greater change in angular velocity. You could also do it from a, if it bounces off, there is a bigger change in angular velocity. You can take a torque standpoint, torque times time leads to a bigger change, and you can go that route as well. Okay, I think that covers it all. A good problem covering some important ideas.